At the turn of the century, a new type of energy was being implemented, one involving utilizing the sun's rays. This new green source of energy was not only safer for the environment, but also an example of many electromagnetism principles. But what allows the sun's energy to be harvested? The answer lies in the structure of the solar or photovoltaic cells themselves. The most important ingredient in the photovoltaic cells that make up a solar panel is silicon. Silicon is a semiconductor. It exhibits properties between those of conductors and insulators. Each solar cell is typically composed of two layers of silicon packed tightly together. Silicon in its purest form, however, is not a good conductor of electricity. To make generating electricity possible, other elements are added to the layers of silicon in a process called doping. Phosphorus, which has one more electron in its outer shell than silicon, is added to one layer of it, which results in this layer of silicon having many free electrons and thus a negative charge. This layer is said to be composed of N-type silicon. Conversely, boron, which has less electrons in its outer shell than silicon, is added to the outer layer. Since boron has space in its outer shell for more electrons, this layer of silicon can readily accept the electrons, as it has a positively charged openings into which electrons can be added. This positively charged layer of silicon is called P-type silicon.
When these two layers of N-type and P-type silicon are put together, a separation of charge exists, so an electric field exists between the two layers. Electric field points towards negative charges and away from positive charges. Thus, the electric field points from the P-type layer to the N-type layer. Drawn by the electric force of attraction, any free electrons that are not tightly held by the chemical bonds in the N-type layer move in the direction opposite the electric field to fill the positively charged openings in the P-type layer. The area between these two layers in which the electrons are moving is called the depletion zone. As more and more positively charged openings on the P-type layer are filled with free electrons from the N-type layer within the depletion zone, a new imbalance of charge exists. Now, the P-type layer end of depletion zone is clogged with the extra electrons that it gained, while the N-type layer end of the depletion zone is left with positively charged ions as it lost electrons. An imbalance of charges create an internal electric field that points from the positive charges and towards negative charges. Thus, an electric field exists within the depletion zone that points from the N-type layer's end of the depletion zone, which is positively charged, to the P-type layer's end of the depletion zone, which is negatively charged. Since electric fields point from high to low voltage and electrons move towards higher voltage to attain lower potential energy, the extra electrons in the N-type layer outside of the depletion zone can no longer move to fill the positively charged holes that exist outside the depletion zone in the P-type layer.
When a ray of sunlight, which is composed of little bits of electromagnetic energy in discrete quantities called photons, strikes a silicon atom within one of the photovoltaic cells, an energy transfer occurs. The energy from the photon is transferred to one of the electrons in the silicon atom's outer shell. This input of energy excites the electron to the point that it actually leaves the silicon atom. This is called the photoelectric effect. If this electron that is ejected is within close proximity to the electric field that exists in the depletion zone, the electron will move towards higher voltage into the N-type layer. This process occurs over and over as multiple photons excite electrons to the point that they come loose. How can we use this motion of electrons to generate a usable form of electricity? This whole process is summarized in this video from Richard Komp at TED Ed. If two conducting panels are placed around the layers of silicon and a wire is connected on either side of the conducting panels around the silicon layers, these electrons will flow from the N-type layer through the wire and to the P-type layer to fill in the openings left behind by the flow of electrons across the depletion zone into the N-type layer. Since charges are flowing, a current exists. Specifically, we have a direct current, or DC. When many photovoltaic cells are arranged together to generate a lot of direct current, it can either be used to power devices directly or converted to alternating current, or AC, through a device called an inverter, as electric grids require alternating current for widespread distribution.
While the concepts of electric fields, voltage, and current are crucial to explaining the inner workings of photovoltaic cells, wave interference is also important. In order for a photon of light to transfer energy to the looser electrons in silicon layers, the light must be absorbed. In other words, reflection of the rays of light as they strike the solar cell must be minimized. To minimize reflection and maximize absorption of the light rays from the sun, a thin film of anti-reflective coating is placed over the top of the solar cell. Placing this thin film of anti-reflective coating minimizes reflection via destructive interference, or at the very least, not constructive interference. The index of refraction for this anti-reflective film is higher than that of air, and the index of refraction of silicone is higher than that of that anti-reflective film. Thus, when light strikes the solar cell on its surface, both the ray that reflects off the air film boundary and the ray that reflects off the film silicone boundary experiences a phase shift of pi.
The initial phase difference between the two reflected rays is 2 pi. As a result, both the reflected rays are shifted by half of a wavelength, as one wavelength is equivalent to a phase difference of 2 pi. The ray that reflects off of the bottom boundary travels farther than the ray reflected off of the top boundary. Thus, a path length difference exists between the two waves. Since the wave travels through the film and back again, this path length difference is equal to 2t, where t is the thickness of the film. Through careful calculations, the film can be created to be one of the many possible thicknesses, and thus path length differences that will prevent the two rays from interfering with one another. Destructive interference occurs when the total phase difference for the two reflected rays is equal to an odd multiple of pi, while constructive interference occurs when total phase difference is equal to an even multiple of pi. Thus, the thickness of the film must produce a total phase difference that is not an even multiple of pi, to minimize the reflection and maximize absorption of sunlight. Through thin film interference, the absorption of light by solar cells that is crucial to using solar energy is made possible in minimizing the reflection of sunlight off the solar panel by making use of wave interference.